Good morning, my dear students. Welcome to this session on Structural Analysis 2 subject, Unit 4 of JNTUK syllabus. Right, so we will talk about moment distribution method. So this is one of the methods under the category of displacement methods of analysis. Okay. So in the previous semester, we have started slope deflection method, which is like uh, under structural analysis 1. So you must recall that method before we start this method, moment distribution method, if you want to understand. So prerequisite for this method is a slope deflection method must be known to you, what we have done in that case. Okay, right. Let's proceed for the syllabus that you have in this unit 4. So stiffness and carryover factors are very much required to solve the structural analysis problems with the moment distribution method. Okay, and also distribution factors are required. So you need stiffness and you need carryover factor and you need distribution factor. Okay, so these three must be defined and we shall derive the equations required for calculation of these three factors. Okay, right. Next, we'll take up analysis of continuous beams with and without sinking of supports. So we'll take up analysis of continuous beams, and then we will move to portal frames with and without sway. Okay, and then another method is also introduced in this unit 4. It's called substitute frame analysis by two cycle. Okay, so this is the syllabus of unit 4. Okay, so where you have uh, the required quantities to be defined and as well as the formulas are to be derived. Okay, right. So we will be solving continuous beams as well as portal frames. Right. Okay. So let's go to the introductory content. Right. You see, this is what I was telling, that you need the prior knowledge of slope deflection method. Okay, so analysis of structures by slope deflection methods is taken up in the earlier semester, uh, previous semester of this one. So in case of JNTUK curriculum, it is in second year, second semester. Okay, so slope deflection method, if you recall what we have done in slope deflection method, if you are given a problem in slope deflection method, for example, just as a case of simplest application, just take a continuous beam. Okay, so this is what a continuous beam is. Then if you are asked to solve this beam by slope deflection method, what we have done, that if you just recall. Okay, so some loads acting on this, right? Okay, so this is say continuous beam given to you and asked you to solve by slope deflection method. What we will do, right? We will write slope deflection equations. So MAB, also MBA. So each member has got two slope deflection equations. Similarly, MBC. and MCB. Okay, so these are the slope deflection equations that we will apply, and we will apply joint equilibrium. That means this one, okay, where B has got two members, BA and BC. So joint moment equilibrium equation we will apply. So we'll have an equation, and also moment at A0 is a condition from the hinge. Also moment at C is 0 is the condition. So we'll have three equations, and we will be solving three unknowns. Unknowns are here displacements, because these are displacement methods. So theta A unknown, theta B unknown, and theta C is unknown. So displacements are unknowns. So A doesn't have Y value, so only theta is unknown because it is a support. Even B is also doesn't have deflection, and C point C is also deflection 0 but rotation present. So likewise all three supports have got rotation present, deflection absent. So three unknowns, so we have three equations. I mean sigma mb0 and mab0 and mcb0, three unknowns and three equations. So this is what is a set of simultaneous equations of unknown displacements have to be solved by you in case of slope deflection method. So the number of simultaneous equations will be equal to number of unknowns to be evaluated. This is what I was telling about. So number of unknowns are 3, and simultaneous equations that you form are 3. So there's one need to solve these simultaneous equations to obtain displacements, and once you get theta A, theta B, theta C, then if you substitute into these slope deflection equations back into them, then you will be getting end moments, moment at A, moment at B, and moment at C. Right, that is what. So beam end moments will be getting. So now simultaneous equations can be solved very easily using a computer, but if the number of equations are more than 3, now before the age of computers, this is a very real difficult problem. Okay, so number of equations in case of a multi-storied building is very high. So even if that was already discussed in our earlier slope deflection method problem, also slope deflection method problems when we introduce. So 1 2 3 4, and few just consider a 5-storied building. Okay, and how many unknowns you can expect in this one if you just think of. So one joint, and 2 3 4 5 joints here, and also 5, total 10 joints where rotations are possible. So 10 rotations. Each floor will have its own delta value, floor delta. Okay, it is not the deflection of the support, it is the deflection of the floor. So you have 1 2 3 4 5 floors here, so plus 5 displacement quantities. So total 15 unknowns are required to solve to get the end moments of each beam and column in this simple two-dimensional frame. Okay, don't go for three-dimensional. You can't imagine what happens to the number of unknowns if it is three-dimensional. I'm just taking just a two-dimensional single bay having five-storied. So if you have one more bay, and number of unknowns will be again, 5 plus and 5 more. Okay, so plus 5, it will be adding. Okay, likewise, so the number of unknowns are not just 3, it will be in 15, 20. And if you go for three-dimensional, the number goes to hundreds of unknowns. Okay, so nowadays the buildings are of 20 stories, 30 stories, right? So number of unknowns will be in terms of thousands, not in hundreds even. So you can't imagine them solving by your on paper by your hand calculation. So they are beyond the imagination of hand calculation. So without the computer, to solve these unknowns by slope deflection method is a impossible task. Okay, so that's why you need a method where you can easily handle these simultaneous equations. That is proposed by Hardy Cross in 1932. So the method name is moment distribution method. So what he has done is it's very simple. He has simplified the procedure of solving these simultaneous equations. To skip this part, the very difficult part in this one is solving the simultaneous equations. That part, if you have to skip it, replace with some easy way, and you can easily solve the structure. That is what is his thinking. So to replace that part of solving simultaneous equations, so he proposed moment distribution method, which is also known as method of successive approximations. Okay, so this method involves the approximate solution. Unlike the slope deflection equation, you get the exact solution, whereas moment distribution method, you can fix the percentage of error that the structure internal forces shall have. So we can fix the percentage of error, the range of error that we get in the values. Okay, so understood. So moment distribution method is nothing but now solving the simultaneous equations that you are getting from slope deflection method in a different way by using method of successive approximations. Okay, so that is the simple uh, defined how you define moment distribution method. Okay, right. So accuracy you can fix on your own. So if you want the values to be of accuracy to the level of 0.1 or to the accuracy level of 0.01, so it's your choice. Okay. So moment distribution has become very popular. Reason I told you that the slope deflection method, there is a difficulty to solve simultaneous equations if they are more in number. That's why the moment distribution where the simultaneous equation solving is replaced with the distribution process. That's why the distribution process by the way of method of successive approximations. That's why it has become very popular. Okay, so it is very simple method and being used even today for the preliminary analysis of small structures by the practicing engineers on a drawing sheet. Okay, it is being still taught in the classroom for the simplicity and physical insight it gives into the analyst, even though stiffness method is available today. Okay, and even the recent times, even this stiffness method is also replaced by the method called finite element method, FEM. So until recent times, like maybe at 20 years back, let us say 20 years back, it was stiffness method. The softwares were using stiffness method. So they're slowly, softwares are slowly shifting to finite element method. Okay, so maybe 10 to 15 years uh, from recent times, like 10 to 15 years back, they are being moving to finite element method. Okay, right. Had the computers not emerged, that was I was telling. So computers, if they are not there, the moment distribution method would have been the most popular method today. Okay, if computers were not being you know, uh, there in as in the popularity that they have achieved today. Okay, right. So this is the information regarding moment distribution method. What it is, what way it is advantageous, why we are still being still being taught in the class, and what is its importance. Okay, so moment distribution method is nothing but the method proposed by Hardy Cross to solve the simultaneous equations that are being developed by slope deflection method by using the distribution process uh, with the help of successive approximations, which made the method very simple in nature. Okay, right. So these are some of the fixed end moments that are required for you uh, to proceed for the analysis of structures. Okay. So these list of fixed end moments, we even had them when you were in SA1 structural analysis one, when we were teaching. These fixed end moments were being noted. Okay, so I think I need not tell you once again that you just refer back your structural analysis one slope deflection method where you find these fixed end moments. Okay, right. Okay, so this is about the introductory content required for you to move on to the next session. So in the next session, we will talk about all these quantities required for the method, moment distribution method. Okay, thank you.